Io qui Margherita, quando vuoi partiamo. Welcome back everyone. Now before leaving the word back to Simon, just a little thing I want to remember you all. This evening, starting 9 p.m., we have PyRiddle. PyRiddle is most sought after and also feared event is in Europython. You have to solve a riddle and you can win Mac Air Pro for free. It's not that bad, other than boast how smart you are. We know you all like to boast how smart you are. I mean, let's admit it. And so you can go there from this hotel and attend to this event. Now back to our teacher.
Yeah, that sounds good. So we stopped at the non-destructive recursive solution before the coffee break, I believe. So next is a little bit more tricky exercise. We should try and write a new solution with satisfying the same set of constraints, keeping in mind that we want a non-destructive and non-recursive solution. So the general pattern, I think, here is that this is a little cleaner because it uses recursion. The next one will be a little more meaty depending on what you choose to have in there. And there are many ways of solving this if you don't resort to recursion. So obviously the non-destructive bit can be taken care of through many ways. You can copy the whole thing at the beginning and then work with it, or you can keep copying bits of it rather than copying the whole thing up front, saving a little bit of RAM. So it's a question of how you choose to traverse that nested list. So please choose whatever feels natural to you and write a non-destructive, non-recursive one. It's the same problem as before, so the set of assertions is flat in the list. The non-destructive bit should be there, so the this test should pass, and we have one solution so far, which is non-destructive but uses recursion. But I want you to write what feels natural solution in Python, not using recursion. Also, if you do it really quickly, try to assess what's the characteristics of your solution are, how it behaves memory-wise, for example. What's the worst case? Is it going to have a large memory footprint? How does it scale with the nestedness of the list? Basically, try to think about stuff like that when you write. Mm-hmm. Any more questions?
it could go. Try a little bit if it goes down.
One.
Okay.
Excellent.
Okay.
Thank you. That's good.
Allora, vedi, io sto facendo la prova, il microfono sto facendo la prova con lo speaker.
So we had some.
Adesso lo sentite, mi confermi? Ok.
Cool. Very good. So how did it go? Did everyone solve the this one, or how many people wrote a non-recursive, non-destructive that satisfied the constraints? Fantastic. What were memory requirements like? Worst case and average case? Double in the worst case. If basically it's a list, that contains just atomic objects, right? And if it's arbitrarily nested, it depends on the load, how well they're distributed, right? Okay, so I'm just gonna quickly go through this solution that I came up with, which I've forgotten all about because it's quite involved. But so I've defined an auxiliary function called a reverse shell copy of a list, so that I don't copy all the sublists. And then I use the stack data structure, like so I've basically this is a work. I've used the list, but I've used it in such a way so I can use pop, which is quite efficient. So basically what I do, while there is work to do, I take the head of the stack, if it is an instance of a list. So let's see. So what happens if the head is the instance of a list? We do. Let's see, it works. So we do a pop again, and this is a head, and we append it to the work data structure, and then if it is an instance of a list itself, then we append it to a stack, but we append a reverse shell copy again. So this particular solution is quite a messy one, but it doesn't copy the whole list. It copies just the top level of that list. So it doesn't copy constituents of the list. So potentially you can process more with it. But admittedly, it'll be hard to maintain and modify, and so no wonder I forgot all about it. So next is a destructive non-recursive one. So let's see what we potentially gonna do here. I'm just gonna show it because it's quite simple, and you probably have written something like that already. So basically, if we allow ourselves to destroy the data structures that we pass in, we could just keep populating the result list with what we pop, and then in the end we could just reverse the result. So this is a little less messy, and still has the nice property of not increasing the memory overhead, but obviously we have a side effect that it'll destroy what we pass into it. Yeah. Well, I'm not. I have not specified memory requirements for this, but for some reason I wanted this not to have a full-blown copy of the data structures that you pass in, because then if in the case where you have a limited amount of RAM available, you will basically be able to work with smaller lists rather than, yeah. Yeah, that's yeah, sure. So that's a good point. So now corresponding Haskell solutions. The very first one that we've solved using the using the non-destructive recursive solution. So here the basic problem with Haskell and solving this is that Haskell lists are homogeneous. So obviously we can't even construct something similar to Python easily. So basically what we end up doing is we have a user-defined data type which we call nested list. That has a couple of constructors. It has the LM, which stands for element constructor. That has an element of type A, and then it has a list constructor, which is a list of nested lists of type A. So if you introduce this data type in the following function, which basically takes a nested list data type, I could have written it in a more generic fashion, but I've used int here. So so what it does, it maps nested lists holding ints onto a list of ints. So again, it's defined in 2 lines. So if we pattern match on the first argument, and if the first argument is an element, then we bind what's inside the constructor to X, and then we simply return a list containing that element. Otherwise, the only other choice is left, because there are just 2 constructors, is that first argument is a list. And in that case, X is now that guy, all of that guy. And basically, in that case, we recurse, we call flatten again on X. But then there is this useful auxiliary function, concatMap. I don't know if you, sorry, I'm just going to put the microphone down for a second. So you can do something like...
1, 2, 3, prova.
So
if you want to free your hands.
Yeah, fantastic.
Charge it again.
Ta-da. Thank you very much, sir. So you can always, in GHCI prompt, type :T and then a function name, and you could see its signature. So that's what it does. It takes a function that maps A's to a list of B's, and then it takes a list of A's and returns a list of B's. So basically, it'll do the flattening bit as well as mapping, which is why it's a convenience function. So that will satisfy the assertions, and you will see the Haskell assertions are, hold on, Haskell assertions are full of constructors for that reason. So next, basically, sorry. Ooh, where did we go? So this place here is where I define a new data type called nested list. And this data type has a type parameter itself. So it can hold something. And that something can be, basically we can construct this data type using ln constructor, or we can construct it using list constructor.
Yeah, but ln, what is it? It's the internal type?
No, it's a user-defined constructor.
So you can, inside of constructor of one type, you can also construct another type.
So a user-defined data structure nested list can be either an element, in which case we precede that element with a constructor. And in that case, constructor, we choose to name it element. We can name it whatever we want. Or it can be a list, right? In which case, there is a bit of tautology here. We just want to differentiate between the atomic value and the list of potentially a mixture of atomic and non-atomic values. And that's the way to do it in Haskell. So it's because it's strictly typed. That's
List is already defined and element is not, right?
Yeah, exactly. So we use in Prelude we already have the list data structure, so you can say like let n equals 1, 2. So, or you can say something like 1, colon 2, colon, I think. So that's already defined. But I could define this user-defined data type myself. So so let's see. So if I don't want to use concatMap, it's possible to use the ++ operator here. So what we do, we define a bit more involved flatten, where again this part isn't changed if it's an element. We just return a list containing it. Otherwise, if we pattern match on the list, we further pattern match on the what's inside, and we name the head of it X and the tail XS. And then obviously we need to now do sort of a double recursion. We need to process X, and then we need to process tail of what's inside the list constructor XS. And then if this doesn't actually cover all the cases, so we will have to add the line where there is a list that contains, capital list, perhaps badly named here, containing an empty list here. So I don't know, does this make sense? I guess I shouldn't have called this element list, because then in verbal communication, list can be confused with capital list, can be confused with built-in list in Haskell. So, but that's the way to do it if you want heterogeneous elements inside the list. So the next task is, unless there are questions, is to do another interesting exercise. It's called run length encoding. So the assertions are basically telling us that what we want is we want to encode the data, but now we want the encoding to be lossless. So that, remember when we were doing compress, we actually discarding information about how many elements were repeated in this succession. But now, for example, if we have a list containing 001, we return a list of tuples containing the multiplicity and the value. So if you can try knock this up quickly, whichever feels more natural to you, the recursive, non-recursive, using list comprehension. This is quite an easy exercise. Using the generator. Some people are done already. Yeah, well, you can use group by, exactly. So as you can see, it's just group by, isn't it? The only, I think, distinction is that group by returns as a second element of a tuple an iterator, right? So you probably would need to do a little bit of munging to make it conform to these asserts. So okay, I'm gonna go forward with this. So I just used group by, and I wanted to factor out a bit of functionality into a function that I called pack. So basically it takes the length of the group and the key and returns it as a tuple, and then I just return a pack key group for key in group and group in group by L. So that's using group by. And the same in Haskell. Now we have the homogeneity that we wanted. So it's quite a clean solution here. So again, pack function there is group function, which we now know about, which returns a list of lists. And all we need to do is pass this list into pec function. And then pec function is a function taking the list of entities and returning a tuple containing an int and a representative. So what you take, basically an encode function in this case, is a simple map of whatever group is returning, piped into this function, which basically takes this list and then just packs it. So an interesting thing here is that basically on the left and the right we have omitted actually one argument here because Haskell has this interesting property called carrying of functions, where you can say things like for example the if you have a function x times y. So if you define a simple function that takes makes a product of two, I don't. Can everyone see that? So you could say something like let g equals f of 1. So what happened here? We partially applied the arguments of f and called that a new name g. So now I could say g 10 and return 20. So that's basically carrying at work. So what's going on here is in code actually it's taking a parameter, but it appears as if it doesn't, because what's on the right also takes a parameter, and it's the same. We don't need to even name it, but potentially you could have written in code y map pec dot group y, but it will be a tautology. So unless you really need to name your parameters, you can write it this way. But if you don't, like in this case here, you can omit it. So the take two is, I believe, going back to the heterogeneous lists, where you could try it as a kind of exercise later. Basically, instead of returning a tuple in the case where there is repetition of multiplicity of 1, you just return the element itself, and thereby sending a message that there is just 1. So multiplicity is 1. So for example here, instead of returning for a list of 0, 0, 1, instead of returning a list of tuples containing 2, 0, and 1, 1, I just return 1 here. So which will save a little bit of storage. So this will, again, if we use group by, it's quite a trivial solution in Python. In Haskell, we will need to define more. We will define the list item that can be a single A, or it can be a multiple. And if it's a multiple, then we need to record multiplicity, which we'll use an int to record in. And we don't specify what A is here. So so pec function will look like this. Again, this is unchanged, but what will happen here is that pec will take a list, and if the m is equal 1, like the multiplicity is 1, then we return single and single constructor and positive value. Otherwise, we will return a multiple with multiplicity and value. And this is a where statement that allows to define what we mean by m and v. So m is basically just the length of every constituent of what group returns. And v is head of L. We know the sublists contain identical elements, so first is as good as any. So so the take 3 is a more interesting one. For example, I wanted here to have a deflate, but on the fly. So instead of, if you notice here, we had, since we used the group by function, what it did, it it not fully inflated the list, but it basically partitioned it. It sort of created a list that contains the multiplicity, but also so group by returned a list of tuples where the first element was key and the second element was an iterator that will iterate across the whole subrange of equal elements. So basically to make sure that we don't do that up front, we do it as we go along. I've created this exercise. And so it's a little bit more involved again because there is a little bit of bookkeeping that we need to do. So, but the more you can have a look at it later if you're interested. But the important point here is that if you care about memory and if you have constrained resources, you will have to write more code to satisfy them. So to quickly sum up what this does, basically pack does what it used to do. If multiplicity equal 1, we return value. Otherwise, we return a tuple. So encode accepts a list. And then if it's basically, if the length of it is greater than 1, then we prime this for loop. And then we keep track of the current multiplicity, and we keep incrementing it if the value is the same as what we've recorded. Otherwise, we basically, once we cross the boundary between the same bunch of elements and the different element, we append whatever we've gathered so far by piping it into a pack function, which will return what we want. So that's the solution where we do on-the-fly encoding. And I have done a similar one in Haskell. So you can have a look at it later. It doesn't actually mean that this will run the same way as it reads when it is compiled because of lazy evaluation. So if you feel brave enough, you could try and work out what actually is going on here in terms of how these functions are interacting. Because obviously lazy evaluation will change the way these entities are computed. But it's a nice way of thinking about the problem if you want to think about it in terms of on-the-fly deflation. So a final exercise which is quite interesting is sorting a list by sublist properties, like length, for example, or frequency. So I'm going to show quickly a solution of sorting a list by sublist length. And then this is a solution that uses a library function. So for Haskell, it's similarly simple. We just import a sort by function from data list. And there is this function in data org called comparing. So basically, you define your sort as sort by comparing length. And then again, it takes a list of lists and then will return the list of lists. So these are concise solutions, but they use library functions. So if you now imagine you don't have a library function, like for example in the case where you want to sort by a sublist length frequency. So how about we try to modify this solution to sort by the sublist length frequency. Does it sound exciting enough? Yeah! So how are you going to go about it? Any kind of leads?
What do you mean with stuff?
So basically what I want, I have a list, and list contains sublists. And these sublists can be of varying length. There could be a bunch of sublists of the same length in it,
Yeah.
and they could be all different. So what I want to know up front is how many lists of each length there are. And then the lists that are more frequently appearing in terms of lengths. If we sort in ascending order, which this one is, should come in the end. So we could use the same pattern using sorted function, but I guess the key function, we can't use len anymore. We need to define our own. So can you try and write the key function that will satisfy that? By the way, how do people feel if we overrun a little bit? Are we all hungry, or we could take a short break or continue? 6:30. Well, this is the final exercise, so I have a little bit of more material which I can go over. So, do you know how you're going to go about solving this? No. If anyone feels compelled to state how it's going to work, yeah, go for it.
Probably I would go with the dictionary and simply the length of, or order, I guess the order of dictionary in some terms. The key would be the length.
Yeah. And where would you take this dictionary from? You'll have to construct it up front?
Right.
Okay, so you'll have to work through that list once to obtain this, and then package this dictionary into a function, get the interface right, and then use that sorted L key equals whatever, and this would be the way to do it. So it's reasonably simple. So I guess you could try and look at the Haskell solution as well. For that, it's very similar. So it's a common pattern. So I'm gonna omit the solution, and you could play with it later to make sure we don't run into other talk. So here's the Haskell solution. It's basically the analog of a dictionary in Haskell is map. Is basically exactly what George said, is a map from an int to an int. I just defined these types, so there is more meaning in the name, but so it's a map that maps lengths to frequency. And then I constructed here. You can import data map in Haskell and play around. There are a bunch of constructors there. One of them is from ascending list with whatever function you like to use when you have key collision. So here we obviously want to add keys so that basically we know how many, add values. So we know how many sublists of particular length there are. So and then the solution is just this. So try to basically pull it apart in your spare time and put it all back together and see how it works. Just by adding print statements around here. So, so to summarize this, you've noticed that we've used maps in Haskell and dictionaries in Python. So here, Python solution is basically a dictionary. So I just wanted to talk about Python dictionaries a little bit. So they implemented underneath using a hash table data structure. And a hash table is basically an array of key value pairs. And so it's an associative container. And you have some heuristics that takes a key and maps it onto a position in this array. And basically, for example, if keys are strings, there is a hash function that you invoke on a string and returns something like that on the 32-bit platform. And then you need to make a choice about your array size, and then you mask it with array size -1 to actually get an array index. And if you have a collision, there is some more heuristics that basically keeps perturbing the position until you find an empty location in your array of key value pairs. And then once you found one, you store it there. So to make sure that the performance is good, this data structure is kept 1/3 empty, so that there are not too many collisions and sorry, not collisions rather. There are not too many perturbations. And obviously, since we have to go through this linked perturbation thing, if we remove something in the middle, the rest might not become accessible anymore. So instead of deleting items, we just mark them as dummies. So that's basically a very, very fast implementation overview of Python dictionaries. So the important bit is, though, that the average case insert and lookup in dictionaries are super fast. They are constant time. And that's why we love dictionaries so much. So in Haskell, however, as you noticed, we use maps because maps actually can be implemented as immutable data structures. Even though there are maps that, like, for example, red, black trees in C++ containers, or they are all mutable. But the Haskell implementation uses the bounded balancing trees. And the difference is basically boils down to some asymptotic complexity and performance characteristics. So balanced trees are guarantee that the retrieval and update are done in order of log n time. And the additional benefit of them is the keys are sorted. So if you need sorted keys plus good guaranteed performance, you are better off with trees. Trees, however, use more RAM, even though hash tables, depending on the amount of, depending on the load factor of a hash table, there might be, because remember we had to make a decision about the size up front. There might be a lot of empty slots in our array. But on average, I think in most use cases, trees need more RAM because they have to store 2 pointers to every branch. And also, I'm told that the for low load factors, hash tables have fewer memory reads than trees, so they are more performant. But it's a mutable data structure, and even though on average case, considering that hash function is nice, that has very few collisions, the staggering constant time performance is a very good thing. But the amortized worst case is order of n, because you could always construct a contrived example where basically hash function is such that all the keys end up in the same bin. And then the worst case is order of n. So hash tables versus trees. Trees can be purely functional. Trees require ordering relationship. So if the entities you store, it doesn't make sense for them to be ordered, then hash tables are better. Sometimes hash function is quite a complex thing to evaluate. So for example, when you grow your hash table, if you reached the end of its capacity, then what happens, you need to increase the storage and then rehash everything. So if hash function is very expensive, then it becomes a problem. So here's an interesting quote from Don Stewart and et al. Basically, map is implemented as a balanced binary tree, and comparing to a hash table, it is a much more efficient representation in a language with immutable data. This is the most visible example of how deeply pure functional programming affects how we write code. We choose data structures and algorithms that we can express cleanly, that can perform efficiently. But it's a constraint. So, and then basically I've done a little bit more. I ventured into trying to use hash tables, even though it's a mutable data structure in Haskell. And by reading around, I found out that basically, since mutable data structures is not what Haskell specializes in, you might not find a lot of high-quality code floating around for this. And they do not receive much attention, therefore compiler might not do as good of a job at optimizing them. So if you find an imperative data structure and try to use it from Haskell and find out an awful performance, it might not necessarily reflect the ability of the language. It might reflect the basically the fact that community is not working there as much as working elsewhere. So basically what I did, I took some examples from Don Stewart and Norman Ramsey, took a hash table, pushed 10 million integer pairs on it and performed one lookup. And so the data structure to use is data int-map in this case. And you can have a look at this later on the slides. But the important point is that int-map versus hash table performed comparably in this case. So the int-map is the top solution, took about 8 seconds, and 9 seconds for hash table. So actually, even though the for Haskell, hash tables are not as fast as they could have been. So it actually makes us favor tree-like data structures. So Python solution obviously would be this. So, but the GC versus CPython on this benchmark, you can see that Haskell is actually much slower than CPython. But this is perhaps too harsh because Python dictionary is a C data structure accessed from Python, whereas Haskell is a data structure written in Haskell. So if you want the same kind of deal in Haskell, you could probably try some try to interface to some implemented in C containers. Yeah.
Did you use the Haskell? Did you compile the Haskell or use it from the interpreter? Because
I compiled it with -02. Yeah. So so basically, what I did then, instead of using hash tables written in Haskell, I've took what Don Stewart data 2D array, which is basically, you can read up on it, about it on Wikipedia. It's a fast mutable associative data type that's available. And this is a solution. That's how it looks. Basically not very different from hash table. You just import a different container. And that basically did a much better job at performing one lookup here. So it's now comparable with CPython. And then I found a typical C++ solution as well and benchmarked that. So GC, Python, and Haskell are all around the same mark. So thank you very much. This is the end of my talk. If you have any questions, if you have any propositions regarding the improvement of the solutions, if you found a particularly good one in terms of readability, or if it's very short in terms of number of lines of code, send it to me and I'll include it and post it with the slides. So, are there any questions? I think everybody wants to depart. Unless...
where will you post the slides?
on the Python website, or if you mail me, I can mail it to you back. So, any more questions?
Thanks very much.
No problem. Thank you very much for coming. Very good.